All right, with that, I'd like to introduce Vivienne C. She's a professor at MIT, associate professor at MIT. And Vivienne was she did her PhD at MIT as well, electrical engineering, computer science, and she won the best thesis award at MIT, which is a pretty big thing to do. That's a lot of smart folks at MIT. So congratulations on that one.
Yeah,
she also has won an award that, I mean, there are all kinds of National Academy, probably a few Nobels in the audience, but she's won an award probably a lot of you haven't, which is she shared a Primetime Emmy Award for some of the work she did on video coding. So congratulations on that one as well. She's one of the leading experts in the world in energy-efficient AI, computer vision, and video compression. And she's won a whole host of other awards, but rather than list them all, I'll just let her speak. But Vivienne C. from MIT.
Great. Thank you so much for the intro. All right, so I'm super excited to be here. It's great to hear that there's a whole institute that's focusing on energy efficiency. I've been looking at energy efficiency myself in research for the past, I guess, two decades, from video compression and now looking at AI. So there is going to be some overlap with the data center discussion that we just had, actually. So maybe I don't need to establish this as much anymore, but obviously there's been a huge amount of energy that's been contributing towards computing and communications. This is from a paper in Nature in 2015, I think. Eric probably has more accurate numbers than this, or at least thinks says there's a bit of uncertainty bars around all of this. But general idea is that computing and communications is around 2% of the global demand of energy, and that's comparable to the aviation industry. And then data centers account, in this article, for 1% of global electricity. I think Eric said 2% these days. And this is primarily probably driven by the fact that these projections were made back in 2015, and this is before the whole big surgence of deep neural networks, which is kind of the core technology that's underlying all this artificial intelligence. We also saw earlier today that, in particular, when we look at deep neural networks and how it's grown across the years, this is just in the first kind of 6 years, 2012 to 2018, when it was first picking up. Even during that time, it experienced a 300,000x increase in the amount of compute that it needs. And this is before, this ends here at 2018. This is before all the LLM, generative AI, ChatGPT aspect that's coming along, and that's humongous. We also already heard today that, in terms of translating this into the carbon footprint, this is also quite significant. So if you talk about the carbon emissions for a round-trip flight around the US, it would be about 2,000 pounds, a human life between 11,000 to 36,000, so the lifetime of a vehicle, 126,000. If you just do a training of a transformer, which is 200 million parameters, so nothing like the 65 billion parameters that Chris mentioned, you're talking about already 600,000 pounds of CO2, right? So this is significantly a challenge that we have today. One area of research that we work on also looks at robotics, and so actually, one of the exciting fields in robotics is autonomous vehicles. And so one thing to also be concerned about is how AI is going to be used in the future. So if we think of Facebook. So from this paper from Carol G. Wu from Facebook, the projection was trillions of inferences per day in the data centers. If you think of an autonomous vehicle, typically one of the challenges there is that you need to see around the vehicle, right? So you don't crash into things. So you often have many cameras. To do autonomy, maybe you need something like 10 cameras around the vehicle. You often want them to run at a certain frame rate so you can react to changes in your environment. So let's say between 30 to 60 frames per second would be something that you would like to have. And then also to recognize different types of objects and different functionality or different aspects of your environment, you might have to run multiple neural networks on each of the video streams that are coming in, okay? And it could be video, it could be radar, and so on. So just making these assumptions for now, if you think about one autonomous vehicle driving for 1 hour, you would run almost 22 million inferences. If, let's say, autonomous vehicles actually does take off, and the majority of the vehicles around the world, which is over 1 billion, are autonomous vehicles, then you're talking about 22 quadrillion inferences per hour driven, right? So that's quite substantial. So it's not only important to think about how we're using compute today, but also projecting in the future. Obviously, autonomous vehicles have a lot of benefits as well in terms of safety, but we should also consider the costs of achieving that safety. So it's not to say we shouldn't pursue autonomous vehicles, but we should be aware of the cost of doing that and try to address it sooner than later. Okay, so this is all about compute. I just want to now take kind of for the rest of my talk, I'm going to try and connect compute to carbon emissions. So what are the kind of key components that connect these two aspects? So the first thing we should be asking is, what do we want to compute in general? Right? So this could be whatever the computing demands are, the tasks, how many inferences you need to run, and so like how many times you need to run your neural network. That will feed into what is the actual algorithm that's doing that computation itself. So for example, what is the model that you're going to be using for your deep neural network? The model is the thing that we're talking about, billions of parameters. What does that actually look like? Typically, we refer to that as a workload. And so then the second question is on what kind of hardware. So for example, what kind of computer are you going to be running that on? What kind of server are you going to be running that on? And together, these two aspects, what you're actually computing, so the computing algorithm and then the computing hardware, is basically describing how we do the computation. So that's also something we care about. That's going to affect carbon emissions. And it's going to dictate how much compute energy or how many energy we're going to consume in order to do this computation. Then to connect compute energy to carbon emissions, I think Chris already gave a great overview of that. So it comes from some form of an energy source that you need to convert the carbon into energy, and then you need to deliver the energy to your computing hardware. So there's the delivery aspect and the cooling aspect. So where you do the compute also matters. I should also mention, so we say carbon emissions here, but there's also carbon emissions for the manufacturing of the hardware as well. So we also must consider that if we look holistically at the whole situation. So what I'm going to do now is I'm going to go through each of these steps, and I want to describe what are the factors that impact each of these steps as we put it together. Also, what are the challenges that we face in each of these steps? And then what are the possible solutions? Okay. So let's start with the computing hardware, primarily because that's the closest to my area of expertise. So we want to have more efficient computing hardware, obviously, to meet these demands. The big challenge, though, is that while over the past few decades, every single time we got a new transistor, these transistors were more efficient and faster and more dense, thanks to Moore's law and Dennard scaling. We know that this is actually slowing down. So this, while it was improving in terms of efficiency, cost, speed, over the past decade or so, there's been a significant slowdown. That's because, of course, you're going to hit a limit in terms of how small you can make these transistors and how efficient they are. So as a result, we can't rely on general purpose processors, so for example, CPU, to become faster and more efficient without substantial changes. So, okay, this is a slowdown. And so what we need to do, this is the typical approach now, is to do specialization, right? Or what is often also referred to as domain-specific hardware. We basically need to think about how to build these computers for the ground up for this very specific tasks that you care about. Now, just to back up, because we mentioned video coding and you mentioned the Emmy, these days for all video processing that you have on your phone, it's all very specialized hardware already. So we've been doing this for a long time in terms of specializations for video compression. What is new now is that you also have to do these for other tasks like AI. And one of the challenges is that AI continues to evolve. And so one of the tensions here already that you have is you're going to specialize for AI or deep neural nets, but we know those models will continue to evolve. So how do you balance that specialization with the need for flexibility? Right, so that's one of the, you have a solution, but there's a challenge there too. Because these transistors it's becoming more difficult to make them scale, there's also been a lot of exciting research trying to explore new devices and new materials for computing as well. Okay, so that's also great. But of course, the other thing we need to consider is how does this all impact manufacturing cost? If you build more specialized hardware, does it last for as long as you need it? If there's going to be new algorithms, right? You have to replace your hardware more frequently. That's going to lead to more, embodied carbon emissions. Okay, so taking a step back, the first question we should ask is, well, what consumes the energy? Because that's how we should target our design of this specialized or domain-specific hardware. As it turns out, the energy consumption is dominated by data movement. And this is primarily based on fundamental physics. When you're moving data in a long distance, you're charging up, let's say, a wire, which is going to be a higher capacitor. So you're naturally going to consume more energy. This is illustrated here in a plot from Mark Horowitz, who's from Stanford at ISSCC Keynote. And what this shows is in blue, the energy cost for doing operations like multiplications and additions. You can see obviously multiplications cost more than additions, and as you reduce the precision of the multiplication, so from 32-bit floating point, which allows you to represent many different numbers for a wide range, to something which is smaller like an 8-bit fixed point number, you can save energy there. However, if you look at the energy cost for reading the data, so accessing data from a very small memory, 8 kilobytes of memory, just 32 bits, the energy cost to access that data is going to be more expensive than actually doing the multiplication itself. So think about a multiply. You have 2 inputs, and then you generate 1 output. The energy cost to access each of those inputs and then to store the final output is going to, each of those accesses are going to cost more than doing the multiplication itself. And furthermore, depending on where that data is stored, if the SRAM is on the computer chip, that's 5 picojoules. But if you're putting that data in a DRAM, so memory that's off chip or further away in a larger memory, that energy grows exponentially. So it's like 100x, 200x more. Okay, so the key takeaway here is that if we want to reduce the energy consumption, we need to address data movement, and we need to bring the data closer, and ideally store it in a smaller memory. So there's been a huge amount of research in this space. So I'm just briefly going to talk about some of the work that we've done, as well as how we've realized this. Other people have realized this in actual products. So in our earlier work in Iris, the main focus of designing a specialized chip was to minimize this data movement. And so the idea behind it was that often data that you use, you're going to reuse multiple times just for different operations. So the challenge there was to figure out what order should you access the data so that you could reuse it as many times as possible, and then you could also store it in a small memory on chip so the accessing cost is very low. Okay? So that's the main idea. So we talk about this as data movement or optimizing the data flow. You might hear about this when you read some of the research or literature on this topic. So as a result, this is back in 2016, we showed that we could reduce the cost of a task of image classification under 1/3 of a watt. And then when we compared this to a commercial mobile GPU, it was 10x less energy. And I should say that this particular chip we designed was with an older transistor, 65 nanometers, whereas that mobile GPU, which was a commercial product, was a much more advanced transistor node. I think it was 28 nanometer. Okay? So that's the key idea behind that. And so since then, since we've spoken on specialized hardware, there's been a lot of work from many companies, including the leading data centers like Google and Amazon, really focusing on building their own chips to reduce the energy consumption and also provide higher speed. Because generally speaking, you have a power ceiling based on how much you can cool it that Chris had mentioned. And so if you can be more efficient, then you can process more quickly. Okay, so these are some examples. Another thing, which is more research, but there has been some commercial startups based on it, is that, well, if moving data is expensive, why not bring the computation into the memory itself? So can you do computation with your memory devices? This forces you to do what we call analog computing as opposed to digital computing in order to do the computation within the memory itself. There's a lot of challenges there too, because you tend to be much more sensitive to noise. But nonetheless, that allows you to minimize the data movement itself. And so both IBM, there's actually in academia, there's a lot of research on this, and then nobly from commercial companies, IBM has been doing research in this, and there's been startups like Mythic who have been trying to focus on this technology. Finally, there's the idea of, well, why not, rather than compute with electricity, can you compute with light? The reason for this is that the data movement cost of light is independent of the distance, so it's going to be cheaper to move this around. You can also passively perform multiplications with light by kind of splitting and diverting the light based on what you're trying to multiply it by. And so again, there's been a huge amount of research on this, and there's actually been some companies who also have been working on computing with light as a startup. So this is, I think, some work from Light Matter. And they had a chip that does this. Okay, so that's the computing side from the hardware point of view. So there's a lot of research there. There's also research in terms of changing the algorithm. So I'll go a little bit faster here, be more brief, but because William will talk more about this. But in general, for computing hardware, at a high level, you can take 3 different strategies that people have taken to reduce the complexity of those DNN or deep neural network models. One is what we call pruning, so injecting sparsity. If you can set some of those weights to 0, we know that anything multiplied by 0 is 0, so you can skip that operation. You can also compress and reduce the storage, which again is good because we know data movement contributes to energy. You can design smaller models, so have a more of an efficient network architecture, and then force them to learn from the bigger models. So you train this humongous, let's say that 65 million or 65 billion parameter model, and then you try to distill that knowledge into a smaller model. Or you might try to reduce the precision of the compute that you use. So rather than 32-bit floating point, you might do 8-bit fixed point, or even like a single binary. And that's going to reduce the amount of compute and the amount of storage. Of course, what's really important here is, how does this impact the quality of result? If the accuracy is not good enough, then you don't care about making it efficient, right? So you always have to think at the end of the day, does it actually work? The reason why, AI is taking off right now, or deep neural networks, is because it's actually working. Because the concept of deep neural networks has been around for decades, right? It's just because it works now. So that's really important to make sure it works. In my own research, we've written books about this. So if you really wanted to go deep dive in this, I invite you to kind of check out this book, and we talk about both the hardware and the algorithmic aspects. Finally, where does the compute come from? I think Chris already covered this well. But so first of all, it depends on where you're doing the compute, where in the world you're doing it, what is the carbon intensity of the energy source there. It might vary by region or time of day. And then, of course, the delivery of the energy from the energy source to the data center, it matters in terms of the cooling cost, power conversion, and so on. There's also a decision on whether or not you want to do the compute in the cloud and data center or on your device locally. So in our own research, actually, a lot of our work focuses on on-device computing and the energy efficient there, because you can imagine on your phone, you're much more constrained in terms of energy. But there's a question of, do you have, is the PUE used to deliver or charge up your phone as efficient as in the data center? But also you can maybe distribute, you're going to have your phones more distributed around the world versus one central power hub. Of course, if you want to move your data around to process it in the optimal location, you also have to consider the impact of the communication cost. That also doesn't come for free, right? So there's always trade-offs here. Finally, what to actually compute? Ideally, we saw data movement's expensive, so you want to reduce the amount of data that's needed. There's a lot of data efficient modeling techniques, incorporate prior knowledge. I think William's going to talk about that next. You want to also evaluate the quality of the trade-off. So you really have to think of a cost-benefit evaluation. Is the kind of accuracy increase that you're trying to achieve worth the trade-off of increase in carbon emissions, right? So sometimes you have to do a lot of computing to get a very slight increase in accuracy. Is that really worth it? And finally, you'd like to reduce the number of requests that you have. From a research perspective, that means that you want to make sure your results are much more reproducible. And this is also good for AI research. There was a while that results were not reproducible, and so there was a lot of people trying to repeat experiments, and that was a waste. But in practice, one challenge in terms of demands for compute is obviously Joven's paradox, which basically means as things become more efficient, people use more of it. And so net is going to be still, you actually might even consume more energy than before, which would be terrible, right? So this is something that we also need to consider. Okay, so what are the key takeaways? We've already seen increasing demand of AI, and this directly translates to increase in compute and then the carbon footprint of compute. We can see that there's many efforts for improving energy and carbon efficiency for compute, but there also remains many challenges. So from a researcher's point of view, that's great. That's many exciting research opportunities. Okay, so with that, thank you very much.
Thanks, Vivienne. So, questions for Vivienne. William, you come on up and start setting up. Yeah, Eric.
Very nice talk. I have a slight suggestion. You may be a little cautious about taking claims from commercial companies about their equipment. Just question for you on precision.
Yeah.
So I've asked my friends at the hyperscalers that run these large models, and all of these chips, they have like 8 ninja modes, and yet they never use them. It's like they told them they have to use the higher precision. And like all of these techniques you list, like analog or optical, reduce precisions are not useful for general compute. How do you reconcile
Yeah.
this interest versus the real world situation?
Correct. I think there's two things to consider. So one is it not useful because there's not good enough software support for it, which is another issue, right? So there's often a lot of new exciting hardware platforms, but if you don't make that easily accessible to the user to use it, like if you have to require them to write all this additional extra code just to access that particular precision, that's going to be a problem. So certainly, having a good software stack that allows you to easily compile and utilize those precisions, that'd be useful. In terms of usefulness, in terms of accuracy, because I 100% agree, what you care about is accuracy. It has to be accurate enough for your task. I think there's a couple things to think about. One thing is definitely training these days still requires high precision to basically determine what the weights are of that neural network. There's still a lot of effort in that. That being said, there's been a lot of research and examples actually showing what runs on your phone for inference when you actually have a trained model and use it, that you can go down to, let's say, 8-bit integer precision. So there has been effort, like demonstrations of that commercially being okay. That being said, it's again a matter of understanding when to best utilize this for what aspect of AI. And certainly there's a lot of research trying to also show, can you push the precision? Whether or not that can be adopted in industry, that's for industry to decide. That being said, some of that research is from industry. Like IBM has a lot of publications on low precision training. So there should be some merit, I hope, for that based on their efforts. But yeah.
Okay, thanks. Dave.
Yes, this is a slightly whimsical question, but I think it's an important one. If you project well ahead into the future, where we might have an artificial intelligence computer that is comparable to the human brain,
Yeah.
and although mine used to run at about 30 watts, it's probably a little less today. What, using your grandest hope for improving the efficiency, how is that going to compare to that 30-watt figure?
Yeah, so I think there's a couple aspects in this, right? So this is like kind of moving towards what they call like neuromorphic computing and trying to build the brain and match that. So I'm not a neurologist, so take this with a grain of salt. But I think some of the challenges of bridging these areas, though lots of people are trying to, is one, we don't fully understand how the brain works. So even if you could try and match the brain, like I think there has been work trying to match at the lowest level of how the neurons fire and stuff, but we don't understand how all of that connects. So how do you build hardware that can connect that way? And then the other thing with the brain is that the reason it can also operate so efficiently is that it has huge amount of connectivity, right? All your, billions of neurons are all really tightly connected. We don't have such interconnect right now from building the hardware. You saw, I think, again, in Chris's presentation, talking about like stacking in 3D, right? Your chips, you can kind of talk in 3D. That's already kind of a, improvement, let alone, it's just like if you think about how all the neurons in your brain are connected, being able to support that connectivity is going to be quite challenging. So I'd say that there is that would be like the holy grail in theory, that you could build a chip that's as efficient as your brain, and then there's other challenges there. But yeah.
Is it conceivable that you may need to use biological devices, synthesized biological devices for computing to achieve the efficiencies you will need?
I think there are folks who are looking into that. Whether or not it's feasible is something else. I mean, I always think about something else that another, like Jan LeCun once said that, we build planes, not wings like a bird kind of thing. So sometimes there's a more efficient way to get there, not using the nature's or biological's route. But I mean, I think this is wide open in terms of how to think through this process.
I'm sorry, we got to move on. Sorry about that. Vivienne, thank you so much.
Thank you.
That's really